Ever wonder where your AI compute actually goes? You're paying for massive GPU clusters, but a huge chunk of that power might be disappearing into a digital black hole. This is the hidden cost of AI. When your GPUs are idling during initialization or stalling on slow checkpoints, your ROI isn't just dropping, it's cratering. In a world of limited capacity, every single second of effective training time, or ETT, counts. Today, we're breaking down how Meta optimizes for the 90% ETT milestone. We'll cover how to quantify your system delays, the secrets to slashing trainer initialization times, and how smarter checkpointing can save you hundreds of hours of wasted compute. If you want to stop burning your budget and start maximizing your training performance, you can't afford to miss this. Let's dive into the details right now.
Welcome to This Explainer. Today, we're unpacking exactly how Meta scaled their AI infrastructure by aggressively plugging the leaky bucket of wasted GPU time. We all know that training large models is incredibly resource-intensive, right? But what actually happens when the steady-state training isn't the only thing eating up your compute? We're taking a deep dive into Meta's massive engineering effort to optimize their PyTorch workloads, looking at the specific bottlenecks they faced, and the honestly brilliant solutions they engineered to fix them.
So let's kick things off with a massive question that the whole industry is asking. When you're training large AI models under really tight capacity, where does all that expensive compute time actually go? You might assume that the second a GPU is spun up, it's just immediately and constantly crunching data, calculating gradients and updating weights. But the reality of large-scale infrastructure, it's far, far messier than that.
And here's the core conflict. As these workloads scale up, raw compute power isn't just spent on productive training. It constantly leaks out into the overhead waste of the in-between phases. We're talking about all that time spent on cluster initialization, orchestration, saving checkpoints, dealing with retries, and recovering from hardware failures. Now, obviously, these phases are necessary, but they leave your incredibly expensive GPUs sitting completely idle.
To understand how Meta plugged these leaks across 2024 and 2025, we'll quickly cover 5 things. 1. The hidden cost of AI. 2. Measuring effective training time. 3. Speeding up the start. 4. Smarter checkpoints and shutdowns. And 5. The 90% milestone. Let's jump right into Section 1, the hidden cost of AI. Across the industry, engineering teams are facing this really harsh reality. Improving infrastructure effectiveness actually gets harder as workloads scale. And why is that? It's because the end-to-end runtime absorbs more and more non-training overhead. For years, everybody focused on improving model flops utilization, like kernel optimization, and that's still absolutely vital. But at a massive scale, non-training overhead becomes this complementary massive bottleneck. If you don't optimize the surrounding infrastructure, scaling your model just scales your wasted idle time, turning tiny little drips into massive leaks. Moving on to Section 2, measuring effective training time. You simply cannot optimize what you aren't accurately measuring. So Meta relies on this absolute hero metric called ETT%, or effective training time. It's basically the percentage of total end-to-end wall time that's dedicated to productive training by consuming new data. This metric is just brilliant because it directly pinpoints idleness and failures. It cuts right through the noise and lets engineers prioritize exactly which system leaks need to be patched first. Now, calculating the exact time spent consuming new data across all these different model architectures is, well, it's incredibly complex. So they break the ETT% formula down into measuring 3 specific areas. First, time to start, which is the gap between hardware allocation and processing that very first batch. Second, time to recover, which is exactly how long it takes to restart after a crash. And third, number of failures, tracking total infra interruptions. By minimizing those 3 things, ETT% naturally skyrockets. Next up is Section 3. Speeding up the start. Getting a massive distributed training job off the ground is notoriously slow. To minimize the time a GPU sits idle during trainer initialization, Meta applied 2 key steps. First, communication optimizations. Instead of relying on heavy network calls to build sharding metadata piece by piece, they set it up so each rank builds its section locally using broadcasted data that's already available. Second, pipeline optimizations. They decoupled independent processes so they overlap. It's kind of like a busy kitchen. Instead of waiting for all your ingredients to arrive before preheating the oven, they introduced a fast batch to trigger compilation early, running it right alongside the actual data fetch. And hey, speaking of compilation, PyTorch 2 compile times were a massive bottleneck.
by consolidating components like the inductor, Triton bundler, and auto-tune settings into a single shareable archive called megacache. They dramatically reduced repeated remote server requests. This one single innovation slashed average PT2 compile time across their fleet by about 40%. That is a game changer. But, compiling once really isn't enough if dynamic shapes force the system to just keep recompiling on the fly. So they partnered with the open source PyTorch team to build a super user-friendly tool called Torch Compile Dynamic Sources. This lets engineers easily mark parameters or integers as dynamic using regular expressions, all without rewriting underlying code. It decisively patched a heavy compute leak caused by unnecessary recompilations mid-run. All right, let's head into section 4, smarter checkpoints and shutdowns. Because even a perfectly started job needs to save its progress, right? But here's the catch. While checkpoints are absolutely vital for recovering from hardware or software failures, generating them actively blocks GPU training. You literally have to pause the entire system to take this snapshot, forcing your extremely expensive hardware to sit entirely idle while massive amounts of memory are written to storage. Engineers face a really delicate balancing act here. You have to carefully tune that checkpoint interval to minimize two competing forms of waste. First, there's unsaved training time. If you don't checkpoint enough, a crash wipes out hours of work. But then there's checkpoint save blocking time. If you checkpoint too often, your GPUs spend all their time paused, just waiting for saves to finish. It's essentially an optimization math problem based on your specific job failure rate. To drastically lower that actual blocking time, Meta developed async checkpointing and PyTorch native staging. Instead of the GPU waiting around for a super slow upload to network storage, async checkpointing quickly copies the snapshot over to CPU memory. This lets the main GPU trainer process wake back up and resume the training loop immediately, while a background process quietly handles the heavy lifting of the upload. They also completely overhauled the post-training shutdown phase. See, when a model finishes, it needs to be processed and published for inference. Previously, Meta used a trending end model, which tied up the expensive training GPUs to do this processing. But they moved to a standalone publish strategy. Now the training job simply drops an anchor checkpoint and immediately releases the expensive GPUs. A separate processing job then picks up that checkpoint using much cheaper CPU machines to generate the final snapshot. By completely decoupling that standalone model publishing process and moving it over to CPU machines, they successfully patched yet another huge leak in the system. That single architectural shift saved roughly 30 minutes of shutdown time per job. Now, just imagine multiplying 30 minutes of premium GPU time across thousands of jobs. The capacity savings there are literally staggering. And that brings us to our final section, number 5, the 90% milestone. You can build the most efficient system in the world, but a software regression or bad scheduling can just ruin it overnight. To protect these hard-won efficiency gains, dedicated teams built really strict dashboards for continuous component-level observability. They actively monitor time to start, unsaved training time, and checkpoint blocking time. This ensures that new job preemptions or service bugs don't suddenly crack the bucket again. They even rolled out new scheduling algorithms to lower job preemption ratios without hurting user quotas. Through the deployment of over 40 distinct new technologies, from megacache to async checkpointing to CPU-based model publishing, Meta achieved a massive milestone by the end of 2025. They successfully pushed their offline training effective training time past a staggering 90%. That means 90 cents of every compute dollar is directly advancing the model, with less than 10% lost to infrastructure overhead. Meta's journey really proves that just throwing more raw compute at a problem isn't a silver bullet. You have to obsess over the margins. By rethinking how initialization, compiling, checkpointing, and publishing all interact with the hardware, they unlocked massive hidden capacity. So ultimately, what is the in-between bottleneck secretly draining your AI workloads? Finding that leak and patching it just might be your most profitable engineering challenge this year.